The question?
I wanted to ask, like, we have on fMRI also the GLM part. Will it also be included into fMRI? Is that, for example, what we learn in statistics or regarding GLM or not?
Let's discuss that next week. But so the slides, essentially the slides that we did, this is the fMRI oral exam. What we did on fMRI in without slides, that's statistics.
Oh, okay.
But of course you should learn everything. But we can discuss that in detail next week. Okay, so then we have now everything in place actually to now get to PPI. Because PPI is essentially just uncover with interaction. And then of course the question is what the different factors are and how the whole thing is applied. So the first thing is that we, of course, again have a discrete factor. Let's start with PPI then. The discrete factor that can be one or multiple, refers to some cognitive process, physiological factor, whatever. This is essentially a task factor. So discrete factor is something like task or stimulus or whatever. So you know that you can do different forms of fMRI experiments where people, for example, attend to certain things during one part of the experiment and attend to different things at a different part of the experiment, or they do a decision task in some parts of the experiment and then do a memory task in certain parts of the experiment, or you present them different kinds of stimuli, houses during certain parts and then faces during the other parts. But the important thing is that you have in your experimental design, in a PPI, you have a discrete factor with various levels. Of course, you can also generalize this if you really want to a continuous form, but the typical thing still for PPI designs is that you have something discrete with multiple levels. The thing that you read in the SPM literature about is always this attention to motion versus attention to color example. So whether you have these motion dot stimuli of varying color and varying motion, and then people were told to attend to either the color or the motion of these dot stimuli. That's the prototypical SPM example. For a long time there was just PPI, which essentially always use two conditions, and then since not that long ago, I think 2012, there's something called GPPI. That's a paper by, that's now always cited for PPI, what's his name, Donald McLaren, which essentially just says what I've just previously shown you, so that in an ANOVA you also can have multiple factors, and then you have multiple columns with zeros and ones. But the important thing is that you have a discrete factor, and that this discrete factor is happening at certain points of the experiment. Yeah, so typical thing would be here you start scanning, here you end scanning, and here during these periods people attend to motion. So this is attend to motion, and in the remaining periods people attend to color. Something like this. Two tasks, two different tasks, a cognitive factor or a psychological factor. It's of course, I would rather call it a cognitive factor, but the whole thing is called psychophysiological interaction, so it makes sense to call this the psychological factor. But it's a task or stimulus factor. That's one thing. So people go into the scanner and do a task, either memory and decision making or whatever you can think of. The other thing is that you of course need your continuous factor or your independent variable with continuous values. And that's actually the MRI time series of what is called a seed voxel. So what happens there is that you acquire the data from the entire brain, and then you decide for a certain area of the brain that you call your seed region or your whatever. You call that whatever you like. Usually it's called seed voxel in this context. You extract the MR signal of seed voxel, which is then a unitarily varying thing over time, and that's your values of the continuous factor. And then, maybe to finish this here, you also form the interaction of these two. And as we've seen previously, if you want to model the interaction, essentially the interaction regressor looks like the product of these 0 and 1 discrete factor levels, or this column of zeros and ones, multiplied with the continuous factor. Yeah, so just bring that back. So what I mean is, currently we have now introduced something like this as the task factor. We have introduced something like this as the time series of the seed voxel. And now we need to model the interaction. We need a regressor that looks like the product, so the pointwise product between this column and this column. So let's also do this to form the regressor. So we would have something here, and something here. So that would be the interaction regressor. And 21st century university can automatically bring down these things. So to have a representation that looks a little bit nicer, let's go here. So what I've just introduced is now again in design matrix form shown here. So in the design matrix we also include a run specific constant, but then we have the times when the participant does a certain task and it doesn't do the other task. So if you think about the design matrix that we developed for the for the ANCOVA with interaction, we only had one of these things here. So we only had this, and then a young group and old group, and the alcohol values and the interaction regressor. Now, of course, in a first level fMRI design, commonly you not only have people perform the one task once and the other task once, and then you have a new run, but commonly you have these blocks of, like, I don't know, 30 seconds where they do something and then they change. So this is why I have more repetitions here. So you have this again, this again, this again, and this again. This is then referred to as the psychological factor, cognitive factor, whatever, but psychological for psychophysiological interaction. The time series of a voxel that is extracted and which is simulated here, but you can view this as extracted from a certain seed voxel, that's called the physiological factor. It's the time series, and that's put in there as the values of the continuous vector, and then the interaction is formed. There are two things, or at least one thing I should say about doing taking the MR signal. So in the original paper on PPIs, that was what it was exactly done. So that basically was just the acquired MR signal, and this was the regressor then, and this was the pointwise product. There is a paper by Gittelmann from 2003 that makes the following point. If there's some interaction happening in the brain between different regions, this interaction does not happen at the level of the bold signal, because it's not that some area of the brain is reading the bold signal from another area, but it's happening at the neural level. So what they then introduce in SPM is a deconvolution step that uses the bold hemodynamic response function to convert the observed MR signal to some underlying neural function based on just using the basic hemodynamic response function. You know this direction the other way around, right? We have discussed that at length. And then forming the interaction regressor by convolving, so by first computing the interaction regressor at the neural level by multiplying pointwise this blue one with this one, and then convolving this again. Conceptually, this is not important. So this is just, conceptually it's very important and not important at the same time, because in the end you again have the regressor at the bold level in the design matrix, because you try to explain bold data, but you formed the regressor where it's a little bit more appropriate if you think biologically about the brain. So that's the design matrix. And again, I think this is shown here. So in black, you have the psychological main effect or psychological factor. So you see the black line that goes up and down like it does in the design matrix. This is just, again, the time series view of the design matrix, nothing new. Then you have the physiological main effect. So in blue, you have the what you actually have as a column here. Now the question is, of course, what do you do with this design matrix, and what is your data? Yeah? So this was so far, this is the design matrix. So that's the X. Now the question is, what is the data? And the data is, like always in fMRI, it's the time series of each and every voxel. Yeah? So you have for each, it's the typical mass univariate analysis. So for each voxel you have a time series, and you use the same design matrix to assess the effects of the there's a question? No? So you do a mass univariate analysis, you use the same design matrix for each and every voxel. So what you are doing by this is that you try to, for each and every voxel now, these are the other voxels, essentially you look at their data. These are the different time series from the different voxels, and you look at their covariation with the seed voxel. That would be the main effect of, or the main physiological effect, the physiological factor. You look for the covariation with that, and you have the possibility to test for an interaction. So to test whether the covariation of this voxel, for example, with the time series of the seed voxel changes as a function of the physiological vector. Yeah. So for each, and you can assess that and test that because you have an interaction parameter for each and every voxel, because you use the same design models for each and every voxel. It's a mass univariate way. You can test for the interaction between the time series of the seed voxel and the physiological factor for each and every voxel. And then the typical outcome of a psychophysiological interaction analysis is then a map that shows as significant those regions, let's say here in the parietal sulcus, that show a significant, let's say a large, if you don't want to go into testing, show a large interaction effect with the time series of a given seed voxel and the psychological factor. Yeah. So again, because that was not that nicely formulated, let's have a look here again. So we use this design matrix to explain the data of each and every voxel, of course also the seed voxel. One example voxel is shown here. That's the red one, where I used the following parameters. For the offset, I used 1. For the main effect, the psychological main effect, I used 0.5. For the physiological main effect, I used 0.5. And for the interaction regressor, I used a -1. Now, if you think of this again from the idea of that essentially an ANCOVA design with one discrete factor and one continuous factor represents simple linear regressions for different groups. The groupings that we have here, like we had old and young previously, the groupings are now our different conditions. Yeah? So we have this condition and this condition. And we have that repeatedly, but of course we can collapse over all the repeated presentations. So that we have one condition and the second condition. Now if I extract, and this is actually how this is done, if I extract the data from the target voxel that I simulated here with these parameters and also estimated them to just show that this is estimable, and look at just the data points as a function of the physiological main effect, that is the time series of the seed voxel, then, and this is the most important thing, then the covariation between the data of the target voxel, for one where the interaction is actually strong, the dependency changes as a function of the condition. As you can see, this is a positive covariation, this is a negative covariation. Meaning, so if you want this as, I don't know, this is a decision task, and this is a memory task, then the coupling, and the coupling meaning the covariation in terms of the time series, yeah? And only that. The coupling between the seed voxel here and let's say this is the target voxel for which the interaction was significant, the coupling changes. What it means is that the covariation between the time series in terms of this simple linear regression changes as a function of condition. Yeah, but that's all that it means. Yeah, so you can also view it this way. You know that there's all this resting state business, and people love to correlate time series of different voxels. So they have one voxel, and then they correlate all the time series from all other voxels with this one voxel, and then they say we found resting state, and it's awesome. And what this is doing is it's looking at this correlation, but it looks whether this correlation changes as a function of the psychological context, or the task, or the stimulus, or the physiological factor, whatever you want to call it. And in this sense can be used as a test of where in the brain the covariation between voxel time courses is affected by the psychological context. And this is what a psychophysiological interaction then is. And all this talk about effective connectivity or whatever, just get rid of it. It's always with respect to one seed voxel. Of course, the covariation pattern might look completely different if you use a different seed voxel. So it definitely depends on what you're correlating with. Of course, there are then very smart people who think, well, let's do this as a seed region, let's use every voxel. And then you have as many of these interaction maps as you have voxels. And it's like, now I have many. In general, so where I did work, where we used psychophysical interactions, we used it for a certain set of seed voxels that were motivated somehow, because if you do it for all of them, then you have many. It's awesome, but yeah. It's also quite similar to what people now do in resting state analysis, where they do dynamic resting state analysis. This whole cognitive neuroscience field is so ridiculous. Anyway, so they do dynamic resting. What they call dynamic resting connectivity is now that they usually you did correlations between over let's say one run. So you had the voxel time series from the entire run, and then you correlated all of them. And then you said, now this is my resting state correlation. Now they don't take the entire run, but only a part, and do a correlation there. And then they shift the window where they do the correlation. And of course, you can also then say, okay, if it's not resting state and I'm doing the correlation, this is then exactly what is shown here. I'm doing the correlation whenever my condition is 1, and then I'm doing the correlation whenever the condition is 2. And then you have this dynamic connectivity. It's not a resting state anymore because you have some task, and you actually should account for your task effects and so on. But it's a very similar direction where these dynamic correlation estimation people now are working on. But this is, of course, also included in the PPI logic. One final thing that one always should say is about PPI, one can either interpret this as we just did, so that the cognitive process or the psychological effect changes the covariation, but you can also view this as that based, because it's kind of this correlation causation question, you can also view that in the sense that the seed region, the target region, so this region, changes its responsiveness to the psychological effect depending on the state of the seed voxel or the physiological effect. Yeah? Because you never know, is one influencing the, so is the psychological effect influencing the covariation, or is the current state of the seed voxel affecting how much this region responds to the cognitive context. And that's PPI essentially. So this shows in the handout. So this is again the ANCOVA view of looking at it, and this is the PPI way of looking at it. If you do it with SPM, I think what you have to specify is a seed voxel, and then it does everything for you. You have to specify the onsets of your psychological factor and the seed voxel, and then it computes a PPI for you. But yeah, that's as much as I can say about this.
Very general question. Do you know about any other approaches to measure connectivity?
Yes, of course I know about many different, no, not many, but so there are two other forms of doing things with connectivity. One is one which I've now forgotten, now I have it, Granger causality. That's a thing that came up kind of 15 years ago or so. That's also a time series thing. And then, of course, the other thing to look at psychologically dependent connectivity in the brain is what is known as dynamic causal modeling. So dynamic causal modeling, which is differential equation modeling of neural systems, that's what people, or at least the London people, call effective connectivity. And this is the topic of the summer term, so we will do all about dynamic causal modeling for fMRI in the summer term. It's a little bit more interesting if you use it for EEG, although Carl has written or published a paper in 2017 that uses the same neural models now also for fMRI, blah, blah, blah. So yes, the thing with, so why connectivity is interesting and more interesting in general than doing GLMs is the basic reason, the most basic motivation for looking at connectivity in neuroimaging is the following. If you do GLMs and you use the same design matrix for this, and specifically also for this, you assume that your faces and houses affect directly, so if you use the design matrix that encodes this for this, you assume that they directly assess all the different parts of the brain. Because you correlate your design identically with the time series of all of these voxels. Now, that this is a good approximation, but also fundamentally flawed, is of course clear from just basic anatomy, where you know that neurons, so that the input, especially if you use visual stimuli, the input is always V1. This is where you get the first response, and then the neural signal must be related to other regions via the neural machinery, and not the visual signal is not directly somehow fed into frontal cortex as assumed by the GLM for fMRI analysis. However, in terms of fMRI analysis, you can also view this massive univariate way of doing things as an approximation to this relay thing. And then if you talk about the time course differences, then of course you need to talk about the delay between different regions, and then the question of whether you can actually recover this with fMRI and so on. But this is and the effects that you get there, this then becomes interesting in DCM for fMRI, or dynamical models for fMRI, which we will actually do in the summertime, actually start with. The problem with DCM is that it comes with this whole variational base overhead, so that suddenly in DCM everybody acts like they were Bayesians because they do model comparison and look at posterior expectations of parameters, but at the same time they use t-tests and classical inference for the GLMs that they use to modulate the regions. And the reason for that is just that Carl implemented this using variation based in inference. It's not a principal reason that DCM and variational Bayes and free energy, they all go together. It's just because it was implemented like this. Yes, so these are connectivity things that importantly interact with, also for DCM, that's one of the one of the important things in DCM, they interact with the psychological context. Yeah? So they are tailored to look at changes in connectivity under varying psychological or behavioral or whatever contexts. General connectivity in fMRI is, of course, correlating different voxel time courses with one another. That's the whole resting state business. Then, of course, you have connectivity in terms of structural connectivity using MRI. The focus of these kind of PPI and DCM analysis is really to see how connectivity changes when different things happen, or look at it the other way around, how changes in connectivity enable psychological processes. Yeah? So with the idea that the interactions between brain regions, this is what cognition is, and if these interactions between brain regions neurally change, then cognitive things happen. The general problem is that all these models, especially, the one that we saw today, this one, and also DCM, so this is kind of going in the right direction of a biophysical model. Also, DCM goes in the very right direction of a biophysical model. So it uses differential equation models like everybody in biophysical modeling. It has a lot of intuitive, biologically meaningful variables in it. The general problem is that they explain changes maybe in a cognitive process depending manner in the physiology, but they cannot do anything. They cannot do cognition. And this is the task for the next 10 years, if I'm allowed to go on there, because you always wish, if you come from psychology and also from medicine, that these models that are being used they are somehow neurocognitively interesting. The thing is, these models, they are biophysically interesting, but they are not really interesting. They don't give you a mechanism how cognition is done. Yeah, they do some covariation between voxel time courses and their interdependence with some task, but they don't give you a story of how the brain does a decision process. And then this is why people love DDMs so much, because they strongly feel that DDMs give you a mechanistic explanation, maybe a little bit misguided there, but at least they believe that. And why more and more, at least in my work, kind of agent-based modeling is interesting, because there you actually see mechanisms that carry out certain psychological tasks. But to combine them with these biophysical, or not even PPI, but real biophysical models like DCM, that's the task for the future. Yeah, more questions.
What exactly do you mean by agent-based models? If you use some algorithms to...
That's now a completely different topic. I can briefly say something about this, but let's first talk about finish PPI. So this is PPI. Questions about PPI?
This doesn't really have any time-dependent information, right? Because you could like switch everything around and you would completely lose the like time ordering, right?
Yes and no. So you mean in terms of that you scramble the time series? Yeah. You can in principle. The thing is, what is done in addition in the whole MRI business, when you apply the GLM to that, is that you model a covariance structure, and this covariance structure accounts for error correlations. So you can do your scrambling if you first whiten the data by accounting for temporal error correlations. Then you can completely scramble things around, yes. So it doesn't have, in the sense that, especially if you look at the covariation between the seed and the data. So if you look at this time point here and this time point here, once you've corrected for possible error correlations, then you could also do this earlier, which is like you see it here. Yeah, you're right. This is also, that being said, this is in particularly if you don't do this deconvolution step. If you do this deconvolution and first get to a neural time series, that maybe where you definitely have, if you then compute the interaction, have a neural time series regressor, and then convolve this again, you have, of course, you could do the same thing in terms of scrambling, but you have it a little bit earlier, because you have the effect, the direct effect, a little bit earlier. Yeah. So you definitely don't have anything like that you account for delays in neural conduction. And this is, so the accounting for delays in neural conduction, this is actually never happening in DCM for fMRI in the standard way, because that's completely not in the model. So essentially this means that the rate of change, so also in DCM, the rate of change at a given point in time in region A directly affects, the state in some region directly at the same point affects the rate of change here. So it's causal, but there's no temporal delay. These temporal delay things you only have, of course you have the overall general delay by means of the hemodynamic response function, but if this is the same everywhere, then you also have none of that. Where you really have temporal delays is in the delay differential equation forms that are used for EEG. And delay differential equation forms are approximations to partial differential equation forms, or partial differential equations which have explicitly an interaction between time and space. Then you really have this thing. But here the ordering and also the effect at a given time point don't matter. This is why this whole, it's actually an important point, because this whole application of GLMs to fMRI is misguided, because GLMs are not time series models, and fMRI data is always a time series in EEG data. And the way this was accounted for in fMRI data analysis is to talk about error correlations and basically make these data temporally dependent in terms of the correlations of the errors. And that's also another topic. That's a good question. Other questions about PPI? No. So then briefly about agent models, because I just mentioned them. But maybe let's stop this recording because nobody else is allowed to hear about agent models. So.